Hello and welcome to Group 16's final submission video for EEE3097S, an electrical and computer engineering design course taken at UCT, convened by the ever-pleasant Professor Amit Kumar Mishra, who has given us the awesome opportunity to work on this project. A little background on this project. So there's a little research group called the Southern Hemisphere Antarctic Research Collaboration. That way we have the really cool acronym SHARC, and they have devised some data collection apparatus called SHARC Buoys. Not this kind of SHARC Buoy. They look a little more like this, right? And I, Rayhaan, and my partner Clyde have been tasked with coming up with compression and encryption systems to transmit this data from a buoy to wherever it needs to go, securely and efficiently. So what limitations do we have? So first of all, we are doing all of our work on our Raspberry Pi and doing data collection using a Pi hat called a Waveshare SenseHat B. And this Waveshare SenseHat B does not contain the same IMU chip that is supposedly being used for the SHARC Buoys. So our data won't be exactly identical, but the sensors are mostly the same, and some of the collected data, given some calibration, should be mostly comparable. And the systems themselves that we've designed, the compression and encryption systems that we've designed, are very modular. So it just requires some interfacing to make it work. So we're doing all of our design using Python on a Raspberry Pi. And I know Python is not the most efficient programming language, but most of our libraries that we used have been compiled in C. So it should be pretty close. It's just more of a scripting language for us at this point. So let's move on to the subsystems. We'll start with my one, the compression subsystem, and we'll begin from the beginning with the requirements. The first requirement is that the 25% lowest Fourier coefficients from the data must be maintained. And the second one is a little bit more implicit by the name compression subsystem. The output data has to take up less space than the input data. And using those two requirements, I went on and started research on a few potential methods for compression. I landed on two, one just being a simple FFT running through a low-pass filter, and the other, much more novel one that I thought of when attending Jamie's talk online. And when I look at the data he's representing, it looked like analog data, of course, because you're representing, I mean, yes, it is digitally stored, but it's a representation of analog data. And another thing that's commonly used as analog data that we deal with almost every day are audio files. And that is an area that's very well researched and well developed, because there's a lot of money in the music industry, for example. So I decided, why don't I look into MP3 compression, since that's hyper efficient and very well, has a lot of support. From there, I started doing some simulation tests, both with the FFT method and the MP3 one. MP3 one came out on top. It was faster, it produced smaller files, and it produced more accurate files. It was just a much better method. The way it works is I take an input array of numbers, I normalize that using, I just normalize the data set between -1 and 1. Then I pass that through into a WAV file using the audio to numpy library, I think. And then I pass that into an MP3, the MP3 compression, and once the output of that is an MP3 file that is substantially compressed. Generally, after you get to a certain point, it gets to about a 30x compression ratio, which is decent. And now I guess I'll be handing over to Clyde. He'll be talking about the encryption subsystem. Over to you, Clyde.
Hello, my name is Clyde, part of Group 16, and I was doing encryption. Basically, for my encryption subsystem, I chose the AES encryption algorithm. So basically what my subsystem does, it gets a file and a password from the management subsystem, and then it encrypts the file and sends it back to the management subsystem for transmission. And in the other SHARC Buoy device that has just received the encrypted file, the management subsystem sends the encryption subsystem a file and the corresponding password, and the subsystem decrypts the file and sends it back to the management system. And yeah, it's basically how my program works. Thank you.
So now we've finally gotten to the point we've all been waiting for, the demo. So in this highly advanced apparatus, you can see our Raspberry Pi with its sense hat on top of it, attached to a power bank to supply power in a remote environment. As you can tell, I am not studying mechanical engineering or mechatronics for that matter. So let's just place this inside the incredibly safe floating device. Just center it a bit. As you can see, it is indeed a SHARC Buoy. I'm going to place it inside the test environment. Let's have a look at that. So there is our SHARC Buoy in its test environment. And from here, we're going to go over to my PC. We are currently SSH'd into the Pi. So over here, we're going to start Python 3 demo2.py. And as you can see on the right here, we have nothing in the FTP folder on my PC. So just press enter. This takes a little bit of a while to start up sometimes. The reason for that is that we have a lot of modular code here that we have in the folder. So it takes a little bit of time to import that. You can see now it's asking us for the batch size. So we're going to go 200 because that takes about 45 seconds. We couldn't get that much faster using Python. Using C, we did get it a bit faster, but we don't know how accurate the data would be because we used some pretty aggressive compiler flags. Let's hit enter there. This doesn't take about 45 seconds, and then from there we should see the stuff be transmitted over to the PC. Let's move back to the actual device and give it a bit of a spin. So we should want to see some yaw data there, a little bit of pitch and roll as well, a little bit of acceleration at the beginning of the spin, and then otherwise we're going to let it become stable over there after a while. I'll throw up the graphs in the video afterwards. The data acquisition is done. As you can see, we just transmitted the CSV data, the input CSV data, just so we can compare the inputs and the outputs. And now it's going to be doing another loop. So let's go and run the undemo file, which is basically what we do to decompress and unencrypt the data. And as you can see, we have 3 files that we unencrypted and decompressed. So let's go to back here, and we write that into a CSV file so that we can easily compare the input and the output. The reason why we have 3 different files here is because of the normalization. As you can see, the next batch came in. So because of the normalization, each thing has varying maximums, and we don't want to lose any data. And yeah, it's just going to keep on transmitting until we stop it. So we'll stop it after the second loop. There we go. That is our demo.